All right, I think we can get started. Welcome everyone to the fourth technical briefing at ICSI. This is going to be conducted in the form of the Zoom webinar. We're not going to be using the cloud or platform. And so I'd like to point out that if you have questions for the speaker, you can put your questions in the Q&A. That's a feature that you should be able to find at the bottom of your Zoom screen. If you push on the Q&A button, it will bring up a dialog box that you can use to post questions. And you know, we can either, I think usually, mostly we've been asking questions at the very end, but Maria has been telling me that she's also fine with answering clarification questions during her presentation. So feel free to post questions there, and I'll be moderating the questions. I'll read them for Maria. The technical briefing today is given by Maria Mikic. She is a software engineering director at Google in their LA office. She's also the site lead of the Google LA office, and she's been an employee of Google since 2004. I think she's had many accomplishments in her career. But what I'd like to point out is that before she became famous, we were both office mates as PhD students at USC. She was the senior PhD student that I looked up to, and I still look up to. With that, she's gonna talk to us about machine learning in Google Ads. And with that, I'll pass the mic to Maria.
Thank you, Sam, for the introduction. So really briefly, before we get started, just to give you a little bit more on my background, as Sam points out, I've been at Google for over 16 years. And all the time I worked in ads. And primarily focusing on various aspects of machine learning, human data labeling as part of this process, but then more recently actually really leading some teams within the Los Angeles office who work on very concrete machine learning problems in Google Ads. And although my background is not in machine learning, and I probably will not be able to answer any of the kind of detailed technical questions, I'll do my best to kind of do this. And the goal of this presentation is to really give you a high level overview of what the kinds of problems that exist in Google Ads and how we go about solving them with machine learning technologies. What are the challenges when we, have to deal with these systems on a continuous basis? And as Sam points out, please interrupt me with questions. I hope you're going to enjoy the talk. So, the digital advertising powers the entire free internet, right? It enables content creators to thrive, the advertisers to reach their customers, and users to access all this content for free. And before we go into the main part of the talk, this is really just a refresher. I assume most of you know where Google Ads show, but here are some examples. If you do a Google search, you will see some ads, at the top of the search results page, and you may see some of them on the right-hand side, which are called product listing ads. If you do an image search, which is a different tab in Google, and you're searching for a visual result, you are also might be seeing some ads in that space. You probably saw some of the ads on YouTube as well, whether they're pre-roll ads when you're watching videos, or they could be on the side as I'm showing here. And as you browse the web, you will encounter many more ads. And although not all of those are actually served by Google, some of them are, like the one that I'm showing in this particular page, right? And then finally, ads are also shown within apps. A lot of apps are coming for free, but actually in order to sort of do the value exchange, the app creators are posting ads at various stages during the app interaction process. So, Google operates at a massive scale. You're probably all aware of this. We have billions of users, and then content creators who are creating, the internet ecosystem. These users are issuing millions of queries. They're uploading billions of videos. They're watching a lot of videos on YouTube. They're interacting with apps, web pages. They're visiting web pages. And then we have advertisers who are continuously updating their inventory, creating new campaigns, updating their budgets, they're changing their targeting methods. And this entire ecosystem needs to really serve ads with very low latency and with high relevance as well. So, how is Google actually successful in this business? So machine learning is at the core of what ads is. We have a lot of data, as I mentioned, web content, users, and queries. And we also have access to data on how users interact with our ads, what ads they click on, which ads they watch, which queries they type. And so we leverage ML or machine learning to power this ecosystem and sustain its existence. The promise of machine learning is that you can teach machines to predict outcomes if you give them enough examples of those outcomes, and that's what we actually do. So I'm going to be covering now in more detail kind of, first of all, the development process, and then going to the details of various machine learning systems throughout ads. So let's look at the high level overview of the machine learning development process. You have these 5 different stages, and during the planning phase, you define the goals of your model. While sort of Google's goals are very ambitious, which I think the Google Ads mission is to delight every user experience with useful ads that power the free internet, machine learning systems tend to work best when the goals are very concrete and measurable. For example, predicting the likelihood of a user clicking on an ad. So to achieve some of these more ambitious goals for our products, we resort to building machine learning systems that help us predict a particular signal that we believe can help us accomplish those higher level goals. So you can also think about this. Sorry, just a second, I need to get some water. You also need to think about the data you can use to build your model. For example, we have what's called ad click logs. This is a place where we store, when a user clicks on an ad, enough information so we can actually train models that predict which ads user might click on next. And in this kind of prepare and analyze the data phase, we might sample the needed data from multiple sources, ad impression logs, which just show us which ads were shown, and then ad click logs, which shows which ads were clicked on, spam logs, which actually identify spammy clicks and things like that. And we prepare the data from those various sources in order to train a new model. And for the remainder of the talk, I will focus on different machine learning models we have throughout the ads ecosystem. So I know Sam likes architecture. This is not necessarily kind of a very interesting architecture view of machine learning systems, and there's a lot of things that are happening inside of these boxes that I won't get into. But at kind of very high level, the simplified version of the ML system, we have data components. And within this section, we have storage, which is typically, as I mentioned, some kind of a log repository. The data ingestion component, pre-processing, and transformation are typically all part of the pipeline that collects, labels, and prepares your training data. The data validation components perform statistical analysis and evaluate training data to ensure that it matches the expectations and that it isn't corrupted in any way. Now we move to the model components, which are green squares in the figure above. And these represent the tools and software components that are used to build, improve, and serve distinct pieces, training and serving. Training includes the model training, tuning, and analysis components. And they provide tools for building and improving model through feature engineering, hyperparameter tuning, and data visualization. And the model validation and evaluation components provide tools for evaluating the effectiveness of a model. Serving includes the model serving components. So once you're happy with your model performance, you move it into the serving phase where actually it interacts with the users. And they also provide tools for pushing the model into production environment where it can be used to make predictions that affect users. And finally, the client and logging components, which are the yellow square in this figure, ensure that the user actions are logged, thereby creating the feedback cycle that allows the system to continuously learn over time. So there are many challenges that the engineers face as they're developing and evolving these models. And I will be touching upon most of these challenges throughout the rest of the talk as I illustrate different machine learning models we have in ads. But I'm just going to pause for a second so you guys can actually read off of the slide, sort of some of these challenges. Okay, so as we are limited on time, I will focus my presentation on just a search ads use case. These are the ads that show up on Google search results. Very similar models, or like, I would say complementary models exist on other Google and partner properties, places like YouTube or display ads, which are ads shown on publisher pages. At the very high level, overview of our serving system, and really this is abstracting away a ton of complexity, is that, as a user types in a query, which you can see on the top left side, which is organic cotton socks, the query is actually propagated to both search backend, which is actually supposed to return search results, and then ads backend, which is supposed to return ads. And then on the other side, advertisers are creating their ads and creatives through this ads database, and the ads backend system interacts with the ads database to select the ads that they're going to serve. So when a user query comes to the Google server, we actually retrieve results for both search results and ads. We serve them to the user. The user may or may not click on an ad. We record that and report it back to the advertiser. So that's kind of like, a very high level overview of what happens for a single user on a single query. So where, in this workflow do we use machine learning? Pretty much everywhere, in ads database, we use it for ads classification, where we actually, as the advertisers are submitting new ads to the system, we apply, policy classifications to make sure that all the ads are adhering to advertising policies as specified by Google, or sort of different tagging of ads for other things that we need later on in the serving. So think about that, sort of while ad may be able to serve on certain properties or in certain locales, it may not be able to serve globally because different countries apply different types of policies for ads, for example. The next place are within the ads backend, which are machine learning systems that are used for selection and ranking of ads. And then there are many other things that I won't be able to get to, which are, things like reporting insights for the advertisers, giving advertiser feedback about what works and what doesn't work. There's a lot of machine learning that happens in that space, but I just won't have the time to go into all those. Okay, so for the remainder of the talk, I will focus on 4 following machine learning systems that are highlighted in green here. I will highlight what these systems do, the challenges they face, and then how do we go about tackling some of those challenges, of course, not all of them. So again, I'm breaking this down into 3 classes of ML ad systems. The filtering system, which actually may prevent certain ads from even entering the system. So this is the ads policy. The targeting machine learning systems, which are doing classifications of queries, pages, and ads, and then matching the eligible set of ads to the queries. And then finally, a ranking system which decides the order in which the ads that are eligible should be shown. There are many other, sort of machine learning systems in each one of these categories, but I'm going to focus on these for the remainder of the talk. So let's start with the filtering machine learning system, which is ads policy. So as I mentioned, before the ads even enter our serving systems, we perform a very important step, which is the filtering of the ads that violate our advertising policies. There is actually a URL at the bottom left of the slide here that is accessible and shows all the different policies that are applied in Google Ads. And this is actually a very kind of complex and continuously evolving space. You can think about, just using the most recent example of the COVID-19 pandemic, how much abuse we started seeing from, shady advertisers who were trying to game the system and sell things like masks that were not, sort of allowed in certain countries, and or we're scamming people. So like quickly developing new policies to prevent that behavior is something that we do in this space. So going back, since policies differ based on both network, meaning like sort of whether or not they're served within Google or served to third-party web pages, and they also differ by country. Not all ads are going to get this, that are violating some type of policy are going to get disabled by default. They may just get labeled so that downstream systems can actually decide whether or not they're eligible for CERT. So I'm just going to talk a little bit about the scale, and on the right hand side, I'm not going to read through it. Like, you know, sort of, you can actually spend a couple of minutes looking through sort of the sheer number of ads that this machine learning system in particular is affecting. And we really have a number of different policies, and each ad is actually checked against all the policies before it's eligible to serve. So in addition to scale, there are other challenges that this particular models face. You know, the first one is latency. The advertisers expect, as they submit new campaigns, that their ads are going to serve within minutes. As I mentioned, you know, there's things like changing landscape. Like, there's election year, all of a sudden there's a lot of election ads. What are we doing here? What are the advertising policies in this space? What happens with COVID-19? Then, you know, for all these machine learning models, precision and recall trade-off is really, really important. Every single bad ad experience can be very costly, but escalations have to be manageable. If you get it wrong, you know, people might appeal, and you need to handle the volume there. I see that there's a question, Sam. If you want to read the question, I'm happy to answer.
Yeah. Fatima Far is asking, thanks for your talk. How the scale is handled? Can you elaborate a bit on that aspect?
Yeah, I will touch upon some aspects of the scale when I get to a second machine learning model. I will, and throughout my talk later on, but I will say one thing, that so far Moore's law has been really, really helpful in that regard. We can actually throw more machines at the problem and solve it. But if you talk, you know, scale comes in many flavors. As I mentioned, you know, sort of, it's not just the data we need to process, but it's also, you know, that the number of policies that we need to develop, as I mentioned, like these precision recall trade-off, that, you know, sort of come with their own flavor of scale, because you need different sources of data for different types of policies. And, you know, just kind of the sheer number of policies does actually add to the scale problem. I know that this doesn't quite answer your question, but you know, I will get to some more kind of, you know, TPU type solutions that we do have for when I get to the second or third machine learning model that I'm going to talk about. So the next one is actually, you know, transparency, which is, you know, can we, as we disable certain ads in the system, can we provide enough information to the advertiser so that they know how to fix the problem if the mistake was honest? But it's really limited, because, you know, there is a potentially huge volume of bad actors out there. And then, you know, creating new policies is really a human intensive, and it requires expertise. Just, you know, for example, when you think about alcohol policy, different countries impose different laws, so you really need legal involvement in this space to really understand how do you do this, you know, at the global scale in a way that actually, you know, satisfies both kind of the user needs, advertiser needs, and at the same time respects the local laws. So, okay, now assuming, how are we doing in time? 20 minutes, this is good. Now assuming that the filtering machine learning system has done its job and prevented the you know, ads that shouldn't be eligible to serve from doing this, we are ready to move into the targeting machine learning systems. So targeting machine learning systems help us narrow down the list of candidate ads for each context. Let's say, you know, in the context of search ads, it's like user query. So user typed a query. Now we need to actually understand which of all the ads that we have are eligible to show for that particular user for that query. Before we actually go into the system that performs this matching, I want to spend a few minutes explaining an important behind the scenes machine learning system that classifies the online content. And actually, this one is of particularly dear to me, because it's one of my teams in Los Angeles that actually does this. So they've worked over the past 13 years on content classification. It's really a collection of machine learning systems that perform binary. For example, you know, is this a particular page about finance? And then taxonomic/concept classification. You know, this page is about travel to Asia. the outputs of this system basically serve as inputs or features to other models that perform the matching and enable both publishers and advertisers to restrict where and which ads are shown. So, you know, if it's not clear after, you know, sort of couple of slides, please stop me and I'll answer questions, but give me a couple of minutes to explain what do I mean by this. So, you know, the system is actually called Rephil, and it has about 1,500 human-defined categories. We actually have a team of linguists who over time have curated a 1,500 nodes taxonomy, which tries to classify the web content into this category. And so, you know, it actually it takes as an input either a user-issued query or a web page or any type of text, and can actually categorize that text into one of these nodes. And this taxonomy exists in over 60 languages. So the input to the system are, you know, web pages from which we extract features such as individual words, as well as n-grams, which are kind of related terms. So, you know, here I have an illustrated example of a web page, which is about a hot dog place in Santa Barbara. And, you know, we actually, as we process this text, we are going to extract different words from the page, but also these n-grams. And then we assemble a lexicon of common words and n-grams. And the nice thing that we can leverage to build this is that we have the corpus of the entire web content as well as user queries. So we can learn over time that words Santa and Barbara co-occur a lot in these pages or on the internet, and that these are likely good n-grams. So it's an unsupervised machine learning system because it actually learns these you know, sort of relationships between words from the web content already. So you think about, like, ground truth is actually the content of the web and user issued queries. So the Rephil model includes about 90,000 machine learned concepts, which we call topics, that represent topics across over 60 languages. So given a piece of text as an input, the system returns a set of concepts that describe what the text is about, as well as the smooth distribution consisting of terms related to those concepts that may or may not appear in the text itself. So, you know, let's say that the text talks about Santa Barbara, but never mentions the word California. From other pages, we know that Santa Barbara is in California. We may be able to return California as additional concept from the Rephil model. So here's some, you know, financial or investing concepts from the Rephil model. So, like, in the background of this table, you actually see a web page that is about investing. And this is, you know, sort of the model output. The concept ID on the left-hand side is really just kind of a numeric identification of a single node in this network, which I will show briefly on this slide and then go back, which basically is a noisy or Bayesian network where every leaf node is a single word or an n-gram. And then these higher level nodes, or, like, you know, sort of non-leaf nodes, are groupings of related words. So, for example, stock and shares are going to be correlated, and then, you know, interest and bonds are going to be correlated as well, right? But basically, ionic, which is also a bond, is not going to be related to stock because it's a different concept altogether. So, you know, concept is just kind of a unique identifier within our network, and then the weight is non-normalized weight, which actually, the higher the weight, the sort of more likely is this bag of words describing that page. So think about, like, you know, Rephil at its very core is trying to, you know, take a web page in its kind of broadest use case and condense it to, you know, a bag of words that best describe this web page. And you can kind of think about that, you know, so if you look at, you know, this investingbonds.com, that things like, you know, index bond, Lehman bond fund, government, ETF is a pretty good kind of summarization of what's on that page. I see there are two questions, so I can, pause.
Yeah, so we have one more question from Leonardo Lita. He is asking, please, how do you get the training data labeled according to the taxonomy?
Sure. I actually, you know, I described the taxonomy. The taxonomy is another, like, it's a different machine learning model than this Rephil, which actually, you know, for the page will return the node in taxonomy. That taxonomy, I think I'm going to get to in a couple of slides, is human curated data. So like we actually ask humans to categorize pages into those nodes. So, but for this particular output where you take a web page and you output these refill concepts, it's completely unsupervised. So there is no human labeled data. So let me actually move a couple of slides ahead. Sam, was there a second question? Sorry.
No.
Okay, yeah, I guess like the counter doesn't reset every time we answer the question. Okay, never mind.
And I'm keeping them there because I thought we might want to revisit them at the
Sure, sounds good. Okay. So let's talk a little bit about challenges. I think I'll get to it in a couple of slides. I might get to the actual human labeling for the taxonomy. The scale, how many pages we've labeled into the taxonomy in a couple of slides. But, you know, just really want to briefly talk about challenges in developing these models. So, you know, we all know that one word can have multiple meanings, like, you know, sort of think about words like bonds, you know, like we already talked about chemical bonds versus like, you know, investment bonds, Jaguar, Apple. You can, you know, start thinking about like, you know, sort of all these words that depending on the context have different meanings. You know, I actually like this example a lot where, you know, I think that this bug has been fixed since, but I think like last year or so, when you asked the Google Assistant, what is the temperature inside? It was actually replying with the temperature in Side, Turkey, because, you know, inside, I guess, is a viable interpretation as well, right? So the other challenge is that is the opposite of the previous one, which is that you can have one meaning but many ways to say it. So, you know, New York City, NY, NYC, and so on and so forth. So like you need to actually somehow understand that all these different ways of saying actually mean the same thing. And then you also need to have some world knowledge. So, you know, here, like some, you know, you should understand that, you know, Eric Garcetti is a mayor of Los Angeles, that Nicki Minaj is a music hip hop star, you know, and these are sort of concepts that you need to, again, learn from, you know, inferring this from the content that is available on the web. So, as I mentioned, you know, for the taxonomy, documents are labeled by trained raters. And we've collected data over these past 13 years as this model has been in, you know, in development and continuous improvement. And so we have about 7 million labeled documents in over 60 languages. So, you know, you might ask yourself, is that a lot? But when you look at kind of 12 million different lexicon terms, you actually end up having, because we have 1,500 categories in 60 languages, that you have 90,000 language category pairs. So many of those categories are going to have less than 100 documents labeled, and the system needs to actually, you know, sort of then predict the category for everything, you know, that it hasn't seen. So, you know, hopefully that somehow answers that last question that was posed. So now that we have content classification, we need to select a set of candidate ads given a query, right? So this is a job of a query keyword scoring machine learning system. So it's a classification model that predicts the query keyword match eligibility. So let's first talk about what a keyword is. When advertisers submit campaigns to Google, they also supply a set of keywords that they would like these ads to target on. Sometimes on behalf of advertisers, we can also automatically extract keywords from their, you know, creative text. And creative is actually a term that means like, you know, the text of the ad. And or we can actually crawl the advertiser web page and we can extract terms from there. And there are machine learning systems that do that. But let's assume that, you know, we already have a certain set of keywords for each ad in the system. Now we need to predict, you know, which of those keywords match the query, right? So there is a system called query keywords that actually performs that match. So that one actually, again, trains on human labeled ground truth. So we actually ask humans to tell us, given, you know, a user type query, which of these keywords are eligible to show, and we train the model based on that data. The features that are inputs to this model are refill concepts that we actually get from the previous stage. So we both classify the query as well as the keywords into those concepts. The feature is also the query itself. the web search salient terms, and then there are syntactic features such as query keyword length or query keyword inverse document frequency, which is like how frequent it shows up on a page and things like that. So there's a lot of features that are parts of this model. So let's talk a little bit about the challenges in developing this query keyword model. In the end, it just produces kind of a score. The higher the score, the better the match, right? But there are more than 500 different ways in which the user can misspell a query, and advertiser want control and quality and coverage. The ground truth data collection in this case is super hard. This is what one of my teams works on this, and you need to start teaching people to think like an advertiser. It's not enough to just ask somebody, is the query and a keyword similar enough, but you need to understand whether or not this is broadening the meaning of the keyword, or it's restricting it and things like that, so you can actually have a really good end-to-end experience. We also have some percentage of the queries are new every day. Should we not serve any ads on them? How do we understand them? How do we find the right matches for those? And then there is continuous updates to the both ad inventory and the keywords. Advertisers continuously play and try to update their campaigns, and you need to actually keep scoring these. And then you need to have a low latency response. Again, millions and millions of ads, users are continuously issuing queries. You need to do this scoring in several milliseconds before the ad is selected for serving. So assuming that now we actually have sort of a set of candidate ads from the whole corpus, we need to also decide how to rank them and which of those ads are going to win the auction. So that brings us to the ranking model. And I, will describe a very, very simplistic version of this model next. So the ranking model is called PCTR, which stands for Predicted Click-Through Rate model. And what PCTR really is that, given a query and some related context, we may know, maybe some previous queries that the user has issued and things like that, and a candidate ad, what is the probability that the current user will click on that ad? So that's the predicted click-through rate model. It's trying to predict this likelihood of a user clicking on an ad. So for the purposes of this talk, I also want to consider a highly simplified auction where all we care for is the advertiser's bid, which is like how much they're willing to pay if a user clicks on their ad, and the probability that the ad is going to get clicked on, which is this PCTR model, right? So let's look at the query skydive and these two candidate ads. Assuming that the left ad has been, the advertiser is bidding 40 cents for a click on this particular ad, and on the right-hand side, the advertiser is bidding 20 cents. And the left ad, this machine learning model has predicted it has a 2% chance of getting clicked, while the right-hand side ad has a chance of getting clicked 5%. You can quickly compute what we call the expected revenue, which in the left-hand side is $0.008, and on the right-hand side is $0.01. So we can just decide to rank these ads by their expected revenue. And furthermore, we can use these relative bids to ask ourselves the next question, which is, what is the minimum that the winning, and like from the left-hand side, from this previous slide, you can see that actually the right ad should be ranked first because the expected revenue is higher, right? So now we can ask ourselves a question like, okay, fine, but what is the minimum bid that advertiser could have bid on and still won the auction? And we do this, and it's called the second price auction, where to win an auction, an ad needs to be more highly ranked than the rest of the ads. And for the remainder of the presentation, because I'm really simplifying, I'm calling this toy ad rank, is really the multiplying the bid with the predicted click-through rate of an ad. So let's talk about now how the auction works when we have these components. So for every query, we retrieve every ad that matches this query. This is what the keyword query match will give us, all the candidate ads. And then for each of those ads, we compute the predicted click-through rate, and then we compute its toy ad rank by multiplying the click-through rate with the bid. And then we rank these ads by toy rank. We choose, up to a certain number of ads to show. Typically, depending on whether you're mobile or on desktop, you will see, anywhere from 3 to 5 ads. And then we second price each ad using its runner-up or using the ad rank threshold. What does it mean is that the advertiser is only going to pay just slightly more than the second position or the ad that is positioned under that ad, because that's the only thing that he would have needed to bid in order to win the auction. And it turns out that actually doing the second price auction really it comes from game theory and helps actually advertisers not try to continuously adjust their bids to pay the minimum, but because we are only asking them to pay to win, they don't adjust their bids, and it helps a lot with changes in our system that continuously happen. So we talked about like what needs to happen. Now let's talk a little bit about how it's done. Give me a second. So during the training phase of this model, we have 2 log sources. One of them is ad impressions, which are, which ads we have shown for a particular query, and ad clicks, which is a different log source, which says, okay, this ad was clicked on. And then, there's like this big magic machine learning box that produces a model. And this model, runs in serving, and actually for every query, produces a probability of all candidate ads. For every query and a set of ads, it produces the probability of user clicking on each one of the ads in the set. So, clearly the challenge in this case is massive scale. So, think about how many queries users issue per day, then how many ads do we actually show to those users, how many users click on those ads. So the input to this magical machine learning box is huge and continuously growing. And then the model itself has very low latency and high queries per second. So it really needs to do this in, I think it's 10 milliseconds is the amount of time it has to actually produce this. And the number of queries it needs to serve is actually serving all of the Google users. So, the first approach to dealing with this scale is to optimize every part of the stack. So on the training side, the efficiency of the system impacts such factors as the types of models you can train, how much training data you can use. And then for serving efficiency, it impacts the number of ads you can score and the types of models you can serve. So we continuously have to, as we're using the system and we're optimizing it, we have to make trade-offs as to, how many ads we can actually score for the auction, how many, different versions of the model we can have running and things like that. So, we do a lot of parallelizations. We optimize the model design itself. We have very efficient features and the way we store them. And then, sort of how we schedule the jobs and how we communicate. And then, of course, there is custom hardware that, Google is continuously innovating on. And on the right-hand side here, we're showing some cloud TPUs that are powering the system. And if I'm not mistaken, definitely within ads, the PCTR model is the highest user of the TPUs within Google Ads. So what are some other challenges that this model faces? So there is a selection bias, of course. The only training data that we see is what we have chosen to show in serving, right? So if you never shown an ad because it doesn't win the auction, how can you predict its click-through rate, right? And so how can we ensure that we are learning the accurate models for the many thousands of candidate ads that we could be showing, but we are not? Then there is also disentangling click-through rate contributions or causality. So if you look at the 2 scenarios I'm showing here, it's really, I'm flipping the ordering of these ads, but it turns out that actually there is an effect of the ordering to the click-through rate. Users are more drawn to the very top ads than they are to the second ad. So like if we only see the ordering shown in scenario 1, how can we compute the probabilities for scenario 2? How much credit should we be giving to the ads versus its position and things like that? And position is really just one of the illustrating factors. There is also things like relevance and page layout and like different formats. Like, I'm showing a very simple, sort of format of these ads, but now you start having, more kind of what we call site links, where within the ad, you can actually navigate more deeply into the web page of the advertiser, or there is an image there. Like all these factors make this problem even more difficult. And then, I already mentioned this, if we have hundreds of ads to show on a given query, how do we balance optimizing for that auction and then exploring new ads, right? So it turns out that we need to strike a balance between a system that can react quickly to new events and one that it's not overly reactive. What happens when we have outlier events? For example, the next installment of a popular video game franchise is announced, or the developer starts running ads on the game's title 1 hour before the announcement. So, these are just some of the challenges in this space. And, in the system that is serving traffic worldwide, some things are always changing. Like there's changes in queries or user behavior. We have a shocking number of unique user queries every day. Skewed data is another huge problem. Like what happens is if a data center goes down and we start non-uniformly losing some training data, like all of a sudden, sort of there's some servers that are down in, South America, and the machine learning system may not be aware of this and can actually skew the training process as well. So I'm trying to be cognizant of time, so I'm going to keep moving. As you saw in some of the ML systems that I described, most of them actually rely on getting labeled data through human evaluation. Another team that I run in Los Angeles is actually doing this. They're basically a team of about 60 engineers, statisticians, and linguists that provide data for all the ads machine learning teams. So really quickly, why do we need labeled data? I mentioned for training and validating the machine learning models. We also do A/B experiments when we have different versions of the models and we want to decide which one to launch. We actually use human evaluation or human labeled data to make those decisions when we're making policy decisions and things like that. So we maintain relationships with multiple vendors to source the remote workers who actually log into our system to label the data. And we call these people raters. Turns out that, raters come from many, with many different traits. So they, speak different languages, they're in different locations, they may have different cultural knowledge that we have or skills. They may be in possession of certain devices. They, we pay them different, depending on locations where they are, the pay rate may differ. And so, one of the challenges we have is actually making sure that we label the data in a cost-effective way and get the highest quality data back from humans. So how do we actually collect the data? It's done through, surveys, which we call evaluations, and raters answer a set of questions. These could be things like relevance or the user intent or how satisfied they might be, sort of whether the user is in market, given some information to, let's say, buy a car. The raters respond through, a variety of UI things like checkboxes and radio buttons and sliders. And, through this process, we try to measure things that you can't infer from user behavior on the web, like things like clicks and queries. And so this system allows for custom evaluations to suite large use cases across many engineering teams. And we always develop new types of evaluations. We have hundreds of different types of evaluations at any point in time in the systems. We have thousands of these raters, millions of evaluations happening on a daily basis.
Maria, quick question. Are these raters like Google employees or they're being outsourced to people outside of Google?
These raters are outsourced. We work with 4 different vendors that supply the workforce globally. So the raters themselves are typically work from home. Although there are some that are in this model called vendor-owned and operated buildings, where actually vendors will ask these people to come into, an office. This is typically done in places such as India or Philippines, where people may not have good enough internet access from their homes, so actually being in an office helps. But for the majority of the workforce is actually people work part-time, work from home through the vendor. Yes.
Thank you.
And, you know, turns out that actually, I love this chart. Data quality really, really matters. Like the sort of the quality of the training data, this chart actually says, you know, that 40% of how your model is going to perform depends on how good your training data is. And then, you know, another 30% is like, how good are you with your features and model structure and tuning? And then 20% is live experiments, and then only 10% is algorithms, right? So this is why we really focus on the training data, because it's really, really important that the labels that we actually create to supply those machine learning systems are of high quality. And it turns out, like, you know, when you're asking hundreds of different questions on, you know, millions of different types of inputs from, like, you know, thousands of different users, that assessing quality is not an easy task. So we resort to some proxies for quality, which is accuracy, which is the correlation of a rater's response to what we call a true response. So for a subset of data points, we can say, okay, we believe that this is the right answer. And then we can measure how often the rater response matches that right response, the response we expect. And then the other measure of accuracy is the agreement. Like if we ask two different raters the same questions, how much do they agree, or how often do they agree with one another? And as I mentioned, that data can affect a lot of things. Are there other questions?
So we have a question. I'm not sure if it's, I'll just read it to you, and you decide if you want to answer it right now, or if you want to answer it at the end. So Priyan Jamshidi is saying, awesome talk, Maria. Thanks for elaborating on the challenges. I was wondering, what were the key challenges in this entangling causal factors for CTR? Did you look at invariant features? Do you also do research in identifying the invariant features in your group or somewhere in Google? Yeah, and then he's saying that they're working in this area, and you know they're interested in the scale aspect. Probably
best to ping me offline, because I can actually connect the person who has the question to folks on the team who are developing this model. This is one model that I have least familiarity with. I know about the challenges, but I don't know exactly how they go about tackling them, so I can't answer the question. But I can, you know, point the attendee to somebody who can.
Okay, thank you.
Sure. And, you know, going back to data quality, it turns out that actually, if you start standardizing the way you ask questions, where, you know, the humans get used to the similar look and feel. So for example, I'm here in the kind of middle column, I'm showing what we call a slider question, where the raters are used to, like, everything that is all the way to the left is bad, and everything that is all the way to the right is good. And in between are kind of various, you know, levels of goodness or badness. Then you get more consistent responses over time. But if you allow, you know, for every type of evaluation, you know, a new person to actually come up with their own way of asking questions, you're going to get, you know, less high data quality, because, you know, they might accidentally, like if you put good stuff on the left and the bad stuff on the right, they may actually get confused and actually give you the wrong answer. And we've seen this in, you know, happening. So it turns out that, you know, even trivial things like, you know, sort of making sure that it's consistent look and feel, that people get used to these things, actually matters. And the other thing that is problematic is context switching. As I mentioned, we actually have hundreds of different types of labeling tasks that these raters perform on a daily basis. And if you actually, you know, keep switching them between different types of tasks where the instructions for what they're supposed to use change all the time, you don't get high data quality. So what we do is actually, we make sure that the rater doesn't get bored, so we don't put them on the same task for forever, but we make sure that they stick on a particular task for at least 30 minutes, which allows them to do at least like a dozen tasks at a time of the same sort before they move to something else. Turns out that it actually helps with data quality. It really helps that we actually have a very big team of statisticians who are continuously coming up with these experiments to help us understand how to improve quality. So we have been collaborating. I just want to touch upon this topic. I know we have, because I've been taking questions, we might have a couple more minutes than an hour. But
Maria, we actually have an hour and a half for this session, so you're perfectly fine. So we've been collaborating with a research group from Stanford and Professor Chris Ree on a technology called Snorke. And, you know, it's spelled like this. And I think, you know, if you just Google it, you will be able to find more information on the web. And really briefly, Snorke is a system for programmatically building and managing training data sets without manual labeling.
So in Snorkel, users can develop large training data sets in hours or days rather than hand labeling them over weeks or months. So the idea is that you have some kind of a domain expert, depending on the data that needs to get labeled. Think about it, like if it's medical data, it could be like a nurse or a doctor. And then this domain expert writes a set of labeling functions, which are basically certain rules that try to prune the whole space of potential, training data. And those labeling functions get fed into this generative model that tries to actually make sure that the labeling functions have good enough coverage of the space, and they output these probabilistic training labels. So just to kind of be more concrete on this, let's say that we're looking at a an advertiser, and we're trying to write a labeling function that is going to, we're trying to build a model that is going to predict whether or not an ad has, alcohol content on it, right? So you may have somebody who is developing this model, just writing a labeling function saying, well, if there is a bottle in the image, it's likely an alcohol ad, right? It's not 100% true. There are going to be, of course, if there's an image in an ad and it has a bottle, there is a higher likelihood than not that it contains an alcohol ad, but, not all bottles are going to be about alcohol, so it's going to get some things wrong. So it basically creates these probabilistic training labels, which, sort of each labeling function is going to have some probability of labeling the data correctly. And that feeds into what is called the noise-aware discriminative model, where actually you train a model, but by knowing that your training labels are not reliable. So you actually have some kind of, confidence in each one of the training examples that is an output from the previous step. That's the basic idea. So on this slide, I'm actually showing you how my team is currently working with folks from the Snorkel team to build kind of an experience for model development within our tool sets. So you have a human on the left-hand side, which actually seeds the model with certain labeling functions. And then we can actually apply those labeling functions to the entire corpus of data through seed expansion. And from there, we actually will have, the corpus labeled through labeling functions, but we won't know exactly how good this is. We can now send a subset of that data for human labeling. And then, we feed this into this label function analysis that tells us whether or not the label is good or not. And if it's not, then we repeat that process. But if it's good, then we actually can proceed into the sort of next step, which is the Snorkel step and probabilistic labels that feed into the TFX. So the idea is that you actually can, with very few human labeled data sets that help you understand how good your seeds are, you can actually get to the model that is reasonably good in performance. So,
Maria, also there's a question here from Hao Xiang Zhang. Besides improving data quality, how do you improve models, such as model chaining, ML models interacting with ML models, anything like that?
This leads me to the next step of my talk, which is about experimentations. So the machine learning models, we do many techniques from, for example, if we just take kind of this previous slide as kind of like, this is the way to get to the alpha version of the model. This model is likely not going to be something that we want to deploy at scale, depending on what type of problem it's solving. But it's a really kind of nice, quick and dirty start to, bootstrapping a model. And from there, you can actually look at model predictions and then do things like active learning to actually label in a more kind of cost-effective way the data that is of interest and improve the model. To give you an example, for example, in the policy space, typically, let's say that we have a policy about hate speech, right? We don't want to actually allow any hate speech to be monetized through Google products. Turns out that, like, if you look at corpus such as YouTube, very few YouTube videos contain hate speech, right? And you know, if you just do a random sample of YouTube videos, you annotate them for hate speech, your machine learning model is not going to have enough positive examples. It's not going to have enough examples of videos which do have hate speech, right? So actually just doing random sampling and human annotation of that data doesn't give you a good model. But if you actually do start writing some of these labeling functions, and you know, sort of you start kind of narrowing things down, so where you can actually zoom into particular areas of the corpus that is of more interest to you, then you can now apply active learning, which is actually like, I will use the outputs of the model to really focus where I'm going to collect more training data to improve the model. That's when you can get much better performance. That's one technique that we use. We also, like, you know, look at kind of the distribution of the model inserting, like what kind of requests it's getting. It turns out that, for example, for mobile apps, if you're trying to classify mobile apps, for example, you can, with, you know, reasonable costs, have the head set of mobile apps, which are the highest, you know, percentage of the user traffic. If you label them manually, your model performs amazingly well. And so the machine learning only hits on the tail of the distribution, or middle and tail of the distribution, but the head is really kind of like the impression rate is so head heavy that it actually makes sense to label manually that stuff. So we do a lot of those types of analysis to decide how to label the data and improve the models. And that leads me into kind of the next sections, which is kind of experimentation, which is—
Wait, there's also one more question. Again, we can take these at the end if
Sure.
if you feel like it. So Fatima Fard is saying, great talk. I have two questions. One, as a native Persian speaker, I see a lot of differences in the results of a query typed in a low resource language compared to English. Is there a specific policies at Google to address this?
Yeah, I think, you know, this is generally, you know, a challenge globally, in that, you know, sort of the way we try to deploy labeling resources, and you know, the machine learning models operate at a global scale. They, depending on what type of, you know, sort of things we're looking at. Can I actually get back to the question? I'm going to ask whoever posted the question to clarify whether or not they're talking about policy challenges, or whether they're talking about relevance. Like, you know, are they concerned that the relevance of the ads is much lower in, you know, Iran or on Persian results than they are in English? Or are they talking about, like, you know, I'm seeing much more policy violations for, because the answer is going to depend on that. Like, once the question is posted, I'll come back to it.
Okay.
Sorry about
there's also a second question here, which is most of the ML models are built in Python, and the execution environment for deploying the model are in different language. I wonder how this challenge is addressed in your team.
So turns out that, yes, most models are being developed in Python and then integrated with TFX, but actually Google internally has a lot of support for you know, launching, deploying models that I unfortunately don't have the slides or the time to actually go into, but it's not a huge challenge. And we have kind of like a reusable infrastructure that a lot of teams piggyback on to, you know, sort of both train the models, but then actually serve models and evolve them over time.
Okay, and we got the clarification from Fatima about the first question. Her question is about the relevance.
The relevance, yeah. So, you know, turns out that actually, you know, depending on the country and the inventory, sometimes, you know, it's really the problem is not necessarily in how the machine learning system is performing, but what is the available inventory in a particular locale. So, you know, I actually am a dual citizen too, and, you know, sometimes do searches when I go back home to Serbia, and similar thing happens. It turns out that actually in Serbia, the bigger part of the problem is that there is not enough advertising inventory to have that kind of selection of what ads to show, right? The budgets are lower, the number of people that are online. So that's definitely part of the problem. I think kind of in terms of the data labeling and is that, you know, it's both a human intensive problem, but it's also a very costly problem. So we, you know, at Google, we resort to things like machine translation for certain languages, and then annotation from, you know, people who speak that translated language. So let's say that, you know, we will translate Persian Persian queries and ads, and then ask English-speaking raters to rate them, there's definitely going to be a loss in quality and meaning. So I think that there are multiple, contributing factors to what you're seeing there, but it's not just the quality of the models, right? Okay, so moving on to kind of how the machine learning systems evolve at Google. This is typically done through experimentation framework. What happens in the A/B test scenario that I have here is that you have a traffic allocation step where a certain portion of the users are going to, when they issue a query, they're going to get one version of a model served to them, and then in the next scenario, when the user issues a query, is going to get a different treatment. So you actually can collect stats over time. So you deploy 2 versions of the model, you let it run for a couple of days, and then you're going to start seeing how many clicks am I getting in both scenarios? What are some user behaviors there? And you can actually use those data points to decide, how much more money am I making in one or the other scenario? And you can use those data points to make a decision whether or not you want to fully launch, version A or B, right? But it turns out that for the most part, that's not sufficient. So we also have, and let me tell you why. Chances of a user typing the same query, or chances of the user typing the same query multiple times and getting different treatments is very low, right? So you are going to have, data that is not fully matchable between these 2 scenarios, right? Like you're going to get a lot of users with treatment A, a lot of users with treatment B, but those treatments are not going to be fully equal. So there is going to be a lot of noise there that is up for interpretation, right? So now we have, at Google, we have a different system that is called counterfactuals, which actually really says, okay, when a user issues a query, which is a scenario on the right-hand side, I'm going to serve it the experiment or the A version of the model, but at the same time I'm going to issue that same query to the B version of the model, and even though user won't see those results, I'm just going to store what would have happened had I actually directed that user to the version B, right? So I have now in my logs, I both have, like, let's say that when the user issues a query, I showed him these 5 ads, but under B treatment, I would have shown him these 5 ads, and I can store both of that information. For information on the left-hand side, I also have the interaction, what the user clicked on. On the right-hand side, I don't have that, but I at least have actually the comparison which ads I would have served in both scenarios, right? And what is nice in this case is that you now actually have an understanding of how the system is performing between those versions on the same set of queries, right? So you can actually, now send, the problem with this is that, these model metrics may impact downstream machine learning systems in unpredictable ways. So like, we can measure clicks, but is that a good proxy to whether or not we're improving user quality? And this is where, again, human evaluation comes in, which is that we can actually assess the quality of those ads, even though the user hasn't clicked on them in both scenarios, and then be able to provide a quality report that says, look, we cannot speculate about the revenue impact, but in terms of quality, on average, scenario B is better than A, for example. We can produce that type of report. And this is something that feeds into kind of the launch decision, and based on other factors, makes a call of which version of the system you're going to deploy. And then there are these things like long-term learning effects, meaning that, sort of user behavior changes over time. Let's say that, version A is showing more ads on average to the user than version B. Well, it turns out that, if those ads are not also good, that users learn that and become more blind to the ads. So, and that effect comes to play, much later than when you're doing the testing. So you need to kind of take into account these, user behavior changes. The other thing is also that advertisers respond to our evolving machine learning systems in different ways. When we change kind of the way we select the ads, or how many ads we show, the advertisers also respond in a way that we cannot predict ahead of time. So there's a lot of complexity that also kind of comes into play when deciding how to evolve these systems that you don't have the data available to you at the moment. So you have to kind of apply, previous knowledge and intuition in some of these cases as well. So I want to close the talk with, sort of a few thoughts of what lies ahead. So as I mentioned throughout the talk, we have been able to throw more machines at these increasingly complex problems and leverage machine learning techniques to really address Google scale. So Google's really visionary investment in developer infrastructure and specialized hardware and compute power has enabled us to sustain growth in this period. With the end of Moore's law, which I'm sure the audience is aware of, we need to innovate in other ways to continue to tackle challenging problems that we have in ads. And I would like to draw your attention to the following quote from the HITL spectrum highlighted in green there. It's worth remembering that human brains have had 100 billion neurons for at least the last 35,000 years. Yet we've learned to do a lot more with the same compute power. The same will hold true with semiconductors. We're going to figure out radically new ways to use those 10 billion transistors. So our teams are already trying to reduce the resources needed to build and deploy machine learning models. But this is something that is going to be increasingly important as we move over the next decade or so. So, just to kind of show you the annual size of the global data sphere, this is kind of how much data is out there on the web. And as you can see, and this chart is only starting in 2010, we ended 2019 with about 40 zettabytes of data, which is expected to grow to, 175 zettabytes by 2025. And, for those, I actually had to look this up. 1 zettabyte is 10 to the 21 bytes, or 1 million petabytes, or 1 trillion terabytes. So I'm going to maybe pause for a second and let you internalize that number. I mean, it's a staggering increase in the amount of data, right? The data gets captured and it's, needs to be replicated. But what does it mean to people or to at least engineers within Google? Our system design have to evolve to make the data the first-class citizens. And then we need to innovate on techniques for storing the data efficiently, processing it scalably, analyzing and generating different insights from the data intelligently. And this is going to be critical. And then having all this data available comes with a lot of responsibility to keep our user information private. And it's critical that we build privacy-aware techniques to analyze this data. And, should we also be thinking about throwing a lot of this data away? I thought there was a question.
Yeah, so there was a question from Puyan Jamshidi. He's asking if he can get the slides or find them somewhere. So of course, these technical briefings are being recorded, so you can find the video later on. But I don't know if Maria is going to be able to share the slides.
I'll get back to Sam on this, so maybe you can ping Sam later. I don't remember whether I can actually just post the slides externally. I don't know. I know that the talk can be recorded. Okay. So, you can ask what will be generating this data? Well, almost all of our devices are already doing this. There is, things like, photos that we take, all the different, even like, aircraft engine is, logging and sending data back as soon as it gets manufactured. So it's like really, every device that we interact with is generating data. I recently upgraded my, kitchen appliances, and it turns out that there is a Wi-Fi connection there and that I can control them remotely. I'm sure they're generating data as well. So
Maria, we have a question related to this from Ishan Rao. Can't we improve the ML models such that it will learn fast and remember more instead of adding more hardware?
That's the hope, that we will not be adding more hardware to tackle this scale. Yes.
Okay, thank you.
So brings me to this really funny slide that we will increasingly be drinking from the data fire hose. However, with all this data, the great responsibility comes to protecting it and being responsible stewards within Google. And I think we take it very seriously. So a lot of this data will belong to our users, and we will need technology innovations to protect the data. Things like federated learning, which I encourage you guys, if you don't know about it, to look it up. And some of this data will belong to our advertisers, and we need to protect them through more innovations in areas such as, ads integrity and ad spam. The other trend that is already proliferating is increasing use of images as a medium of conveying information. Human beings have been doing this since ancient times. And, we have high bandwidth input sensors, which are our eyes, to take this visual input. but the images also tell a better story than the words can. So increasingly, you know, especially as products are becoming more image and video centric. And this is because an image is worth 1,000 words. How many times have I heard this, right? So what is the fueling the growth of the image content? You know, the power devices we always have with us. We are taking, you know, pictures of our world, you know, buildings, families, furniture, wildlife, you name it. But we are continuously capturing the visual representation of our world. Humanity collectively took 1.2 trillion photos back in 2017. And the camera technology keeps evolving. So the understanding and organizing and managing this humongous corpus of data is already a big technology challenge. But there are even bigger challenges that intersect with our ads business, which is, you know, can we build image technologies that allow advertisers to create high quality creatives from pictures that they take? You have a lot of, you know, going back to kind of different countries where you have small businesses that may not have web presence, but they do have a phone and a camera. Maybe they can take pictures of their inventory and actually we can help them, you know, create appealing visual campaigns for their products with, you know, with their kind of technology that they have at their fingertips. And what delightful experiences can we create for our advertisers if they provide us images for products that they sell, right? Another, you know, big trend where Google is already a leader via YouTube is the emergence of ubiquity of videos. Videos are a great way to express yourself. We all know that everybody is, you know, becoming, you know, a YouTuber. I guess, you know, this talk is going on YouTube like in a couple hours. And more of those videos are watched on mobile phones. So should we think about video context in the context of advertising business? I think it's a really important thing. And then of course, you know, things like augmented reality, of course, this, you know, product is no longer looking like this, but it's a natural transition from images and videos to where a user world would be seamlessly incorporated into whatever experience we're trying to create. But it's almost already kind of proliferating in the ad space, like IKEA, Lowe's, and Target already have, you know, built products within their websites with, you know, sort of virtual exploration of the space so that you can visualize things. So it's a natural technology for things like shopping and fashion and furniture and home goods, which are part of Google Ads business. So with that, you know, I can take some set of final questions, but this is what lies ahead for my teams. Thank you.
Thank you, Maria. Great talk. So now we have a chance to ask more questions from Maria. If the attendees have more questions, you can post them in the Q&A box, and, you know, I'll read them. But to get things started, because it might take a while for attendees to type in their questions, I guess a lot of what you talked about today and a lot of what was sort of in the future seem to deal with machine learning or data science, basically. And, you know, ICSI being a software engineering conference, or our skills being in software engineering, and how do you see ICSI community's role, software engineers' role in this future? You know, yeah. I mean, what are your thoughts about that?
Sure. So I think, you know, a lot of, you know, as I mentioned, I've been in ads for a really, really long time, and a lot of these machine learning systems evolved kind of rapidly with, you know, sort of a bunch of talented engineers getting together and solving, you know, a problem that, you know, kind of would fill the gap and improve the serving experience, you know, organically. But turns out that actually, you know, we have a lot of fragmentation within various parts of the ads ecosystem when it comes to how we build and deploy these models. And although, you know, sort of there is a lot of, you know, development infrastructure work within Google that helps us, you know, sort of have tools at our disposal that, you know, monitor these models, you know, help us, you know, sort of address any, you know, production level bugs with them. We are still kind of in, you know, early stages of standardizing ML model development, and actually ways in which we can think about sharing these, I call them foundational machine learning models throughout ads, just as one example. To give you some, you know, examples in this space is that, as I mentioned, the search ads, which was one of the use cases I described, is actually a different serving stack than YouTube ads, right? YouTube ads are actually served differently, but fundamentally, you know, sort of while, you know, search is sort of the journey is a user types a query, you serve some results, and on YouTube users are exploring videos. Ultimately, the kind of content that you need to classify is some combination of text, video, image, and you need to actually do some stuff on that. And turns out that actually, in terms of sharing those fundamental building blocks is for example, that Rephil model that I was talking about, that one is actually shared more broadly, but it's not shared in a systematic way. Like, teams, may say, oh, look, there is this useful feature, I'm just going to deploy it in my model. But, how do I actually, build a infrastructure that allows me to understand what features are available for the data that I'm looking at, what is the most useful data, how do I actually build these models in a way that, reuses as much as possible, is easy to evolve, is actually, scalable, and, is still kind of, as I said, like maybe solved for each particular system in a different way, but there is no standardization. And I think there's a lot of room for, both, resource savings as well as, sort of faster, like think about like, we want faster, better, and cheaper machine learning models. And, there are multiple ways of tackling this, but a common infrastructure that allows you to share these basic building blocks of how these, end-to-end models get composed in the end, right? Like, let's say that I'm trying to, to use that example of an alcohol ad, like I may need to process text to understand what's in the text. I may need to process an image to understand what's in an image. If there's video, I need to process the video. Can I actually share those intermediate outputs from those processing steps so that somebody else looking at that same data and trying to predict something else doesn't have to start from scratch? There is already some signals available to them to build these higher level models, right? Mm-hmm. That's one question. The other one is, how do you efficiently annotate that data? Like, should you be, for every use case, starting from scratch and saying, okay, I'm going to ask humans this question? Or is there a way to say, okay, well, a human is going to look at one, particular piece of the inventory, and they're going to give me 20 different annotations that I can then use to train 20 different models or 20 different variants of the model, right?
Mm-hmm. Okay, thank you.
Sure.
That answers the question. So we have a question from Jack. For ML models used in Google Ads, what are their release engineering process? What kind of requirements, test cases are imposed to those ML models?
It's an excellent question. The release process is fairly involved. Depending on which ML model you're trying to launch, we actually could have multiple versions of the model in existence because different kind of higher level models may depend on them differently. So Rephil is a perfect example. When we want to launch a new version of Rephil, we have couple of, we run a bunch of our regressions to make sure that, the model predictions are, stable, that we believe that, both precision and recall, we do those standard analysis to measure precision and recall and understand what the model is doing. But there is also so many kind of cascading dependencies that exist where even though the new version of the model we are developing, according to our measures, is doing what we believe it should be doing, we also need to understand how it's impacting those higher level models where the output of that model serves as an input to the next level model, right? And so that's where we actually tend to be much more conservative. This is one area of software engineering we'd like to solve. We'd like to actually kind of maintain and sort of serve fewer versions of the model. We'd like actually that the latency between the latest version of the model and all the different systems that use that model is as little as possible. But it's currently not the case. There are certain very critical models that are, sort of, where we are very careful as to how we evolve it, where they may rely on certain kind of more basic models, versions that are 2 years old, for example, right? And this is something that we are aware we would like to address, but it's not an easy task because, as I said, it's not just that you're looking at your ML model end to end, but it's actually, if it's feeding downstream to other models, like what is that impact? And it's not an easy way to assess it.
Thank you. We have a question, seems to be related to the previous question from Haozhang Zhang. What are the general process, if any, on how to tune / improve the ML model quality?
I mean, again, it depends on which model which model you're talking about. Certain models are tuned to high recall, certain models are tuned to high precision. It all depends on what the model is trying to predict. We also do a lot of, especially in the policy space, we do a lot of what we call lead generation processes, where for the model that is in serving, we are actually going to sample a certain set of, high impression new pages and manually review them over and over to make sure, because, one of the challenges is that, a page that today doesn't violate any of Google's policies could violate some of the policies tomorrow. Not because Google policy changes, but because that page changes. But then on top of that, Google policies change and evolve. So it is something that there is a manual process involved. There is also, as I said, depending on what type of model you're dealing with, you sometimes want to tune it for high recall because that's what the focus of the model is, or you want to tune it for high precision, or you want to tune it for some sweet spot in between, right?
Okay, thank you. Puyan Jamshidi is asking, you mentioned about a lot of exciting challenges you envision in the context of advertising and how ML could be relevant. From your personal perspective, what is the grand challenge that you think companies such as Google are now dealing with and you think is relevant and distinguish from other challenges? And then he concludes by saying, thank you so much for a great talk again. Not all people talk about relevant problems, challenges in their talk.
Sure. So, I think that in addition to sort of more, visual inventory and more, just more inventory in general, I think we're dealing with a highly dynamic space and, sort of a lot of user-generated content that is happening more outside of these sort of publicly available data sources. If you think about it, web is a publicly available data source. We can crawl those pages, we can parse them, we can understand them. But more and more interactions are now moving on to mobile devices, and they're siloed within, applications that require, user login, and, this could be private, this could be, sort of, something that the actual application owner doesn't want to share with the advertising entity in order to actually get the ads. So how do you solve these problems like in a user preserving where? How do you actually respect user privacy, but still, do what the user expects, which is actually, I want to have this experience for free, right? So for free means actually, I'm willing to watch some ads in order, or to interact with some ads in order to actually experience this app, or whatever is the sort of online experience that you want to have. And so I think that increasingly we're going to have to figure out ways in which we can provide relevant and useful experience, because in the end, the internet doesn't the internet ecosystem really thrives because the ad experience is there. You would not have publishers who are creating the web content. You would not have app developers who are creating, interesting apps if they couldn't monetize that in some way. And, newer generations are expecting all of those things to come for free, and they're used to actually having ad experiences. But more increasingly, they're also expecting, certain preservation of their privacy rights and things like that. And especially, in European Union, we've seen these things. So I think that increasingly we're going to have to come up with creative ways of either, offering user choices, right? Maybe for certain types of experience, you're willing to actually have a subscription model, or to, have an ad-free experience because you really care about their data. And for certain other experiences, so really giving all players in the ecosystem more choice, but doing it in such a way that preserve. And then I think the other thing is also that, I'm talking to a technical audience that can understand a lot of these challenges. I think, when you go to kind of global set of Google users, explaining to them how, when they see a relevant ad, in their app, and they may have, they may have done a search, 2 days ago somewhere else, how, is how are these different pieces connected? How is their privacy respected? Is a much harder, proposition to make. And really kind of, I think we're going to have to work with various, partners throughout the industry to actually educate the users of the choices that they have available and help them. Nobody reads these like long user consent pages that are out there, and it's not, something that Google has control over. It's really all players in the ecosystem that need to participate, users, content creators, as well as, advertisers, in order to actually kind of arrive at where we would like to be. So.
Great, thank you. Siming Wang says, great talk. Speaking of the generalizability, searching ads is one task. How to generalize to search other things? Do you think knowledge graph is a way to organize and unify knowledge from different domains?
I think, Google's knowledge graph is really an excellent sort of, knowledge graph is one of the kind of core signals that feeds into many of the machine learning models that I was talking about. But when you start thinking about sort of the need to act on various types of behaviors in the internet space, you really need very concrete machine learning models who can make a quick decision on a particular data set really quickly. And this is where, sort of you have to resort to having many, many, many models, each one of them solving a very specific issue, and then them working together to kind of orchestrate this effort. So I don't think that we are going to kind of have, one giant thing that sort of, and increasingly so as we make these decisions, and we're going to have to be more transparent, to all the players into the system, what's happening, right? So like, I think that there are already questions, and Sam's and my sort of academic brother has been working on understanding the machine learning biases that exist out there. Clearly, sort of you need to start explaining why the model made a certain decision. And this is actually an important area of research that we are partnering with several academic institutions to really tackle this problem, because I think it's going to be increasingly important to really understand whether there are biases in the models we already have, and then to actually be able to explain the decisions that these models are making to the players in the ecosystem that care about those decisions.
Great, thank you. And I think the last question is a very appropriate question from Ishan Rao. Can you give some advice to students on how to prepare ourselves in both machine learning and software engineering area?
I think, both. So let me put this question. Let me answer this question this way. I've been working with the human evaluation team for over a decade, and then with the what we call signals team, which is actually really machine learning teams within Google Los Angeles, for about a year. And I think that there is a really nice synergy between sort of software engineering, which should be focused on the infrastructure that is needed to power the machine learning ecosystem, if you will. So there is continuous innovation in this space. How do you actually, like, I think you can possibly, it's like, what are the infrastructure that you need to build better, cheaper, and faster models over time, right? And then, on the flip side, you're going to have machine learning experts who are going to innovate in, feature space engineering, like, sort of the underlying technologies as to how do you actually, develop the sort of the same quality models with fewer data that you need to process, how you can actually, sort of get rid of a lot of data, how you can do this in a privacy preserving way, things like that. So I think that, in terms of preparing, I don't know kind of what sort of the latest university programs exist out there, but I would pick one track and then definitely take some elective courses on the other side. So I think that actually the best engineers at Google are the ones who actually, have expertise in one of the two areas, but have at least a solid familiarity with the other, although they may not be experts. So, the most successful engineers on my team are either machine learning, world-class experts, or software engineers who actually, took a bunch of Coursera courses since they started working at Google and came up to speed on some machine learning stuff. So I guess my answer is a little bit of both, at least.
It sounds like the answer is to stay flexible, right? I mean,
Yes.
I think we both started in software engineering. Now you're doing more machine learning than before. So
Exactly. I had to do it myself, to just kind of be able to understand the problems that the engineers are faced with and to be able to guide them. I had to actually take a couple of Coursera courses in machine learning myself.
yeah. I mean, a lot of the papers at ICSI are also about machine learning. It seems like, I mean,
Yeah.
that's the hot area. Well, I think that's all the time that we had for today's technical briefing. I want to once again thank Maria for a great talk. I mean, it's really nice to have industry talks at ICSI, and I second Puyon's comment that it's nice to be able to hear about the challenges facing the industry. I also want to thank the attendees because this was a very interactive session. We got a lot of good questions.
Yeah.
So thank you, everyone.
Thank
There
you.
is one more technical briefing tomorrow by Miriam Kim. And that's going to be the last technical briefing at this year's ICSI. Thank you.
Bye, everybody.
Bye.